Hello everyone, I'm honored to have the opportunity to speak at this meeting. Today, I would like to present my paper, Fear, a Federated Edge Learning System for Efficient and Privacy-Preserving Mobile Healthcare. In the first part, I'm going to begin with the background, motivation, and challenges of our paper, and then discuss in more detail the specific issues in our design. As we can see in this slide, AI has been rapidly advanced over the past decade and has driven evolution in healthcare. Various tasks such as drug research, diagnosis of disease, and chronic disease prediction can be transformed with more accuracy. The market is rapidly growing, and specifically we target at mobile healthcare. It is very difficult to fully exploit the utility of AI in mobile healthcare with high privacy sensitivity. The utmost challenge is that the decentralized user data created by each mobile device is very sensitive to be shared with for the serious security breach. Here is our survey of medical record breaches in recent years. We could find that the number of leaks has been increasing over the past 5 years, resulting in very huge economic losses of the healthcare industry. As for the way medical records is leaked, hacking incidents and insider threats are two major types. Healthcare providers are not trustworthy as we usually believe. For the sake of privacy security, medical data sharing between patients and hospitals is very sensitive. Each of them become a data island. However, training a model on local dataset with scarce and biased data samples easily results in low quality and poor generalization. For example, in early stage of disease outbreak, such as COVID-19, few samples can be obtained. After the rapid spread, the cases observed in one single hospital are still not representative to cover all the features due to high variability. The second challenge for mobile healthcare is limited resources in mobile medical devices. As your network training is extremely computation intensive, it easily drains the battery and stalls the normal operations of the device. Moreover, with the increasing size and complexity of advanced neural network models, it may even become infeasible to maintain a large model on the resource-limited mobile device. So, what makes a good mobile healthcare system? For this problem, we give three basic properties: high diagnosis accuracy, efficient health monitoring, and record training and privacy preservation. For the three properties, we propose a federated edge learning system. The contributions are summarized as follows. I would like to present them one by one. The first point is efficient health monitoring and model training. The figure shows our system design. It consists of three modules. In this slide, let's focus on the red part or in this figure. To relieve resource burden in mobile devices, we follow the edge computing paradigm and propose to offload health monitoring and model training tasks to the hospital private server. Specifically, we partition the network model into two parts. Instead of directly uploading the wearable device data to the hospital, the mobile device implements the formal part of the model and uploads the output of mid layers and data labels to the hospital servers. The server would regard the noise output of middle layers as input, update the pair width and the BIOS, and send the gradients of loss to noise output as the feedback. The client would update its width and BIOS according to the gradient. In this way, we are allowed to alleviate the computing burden on the mobile medical device and improve the efficiency of health monitoring and model training. We implement a simple prototype system to conduct our experiment and measure the resource consumption at the Android smartphone. Our experiment platform is shown in this slide. We use the smartphone and laptop to emulate the resource-limited mobile medical device and the hospital private servers respectively. We leverage breast cancer data as a private medical dataset and the distribution chain of training and testing samples is given, and we leverage one neural network model shown in this figure to analyze the samples to diagnose whether the breast cancer is benign or malignant. This model consists of one input layer, one output layer, and 6 fully connected layers, and the corresponding activation layers. We measure the CPU process time, total time of model training, virtual memory consumption, and energy consumption on the Android mobile phone. The total training time includes local training time, communication time, and third-party training time. When the number of offloaded layers increase, we can observe that the gradual decrease of CPU process time and the total time of model training during the training process, and the memory consumption and energy consumption also decline. When offloading long layers, it represents the traditional learning paradigm without efficiency consideration, and when the offloading 6 layers, it represents traditional learning paradigm. It represents offloading turtle models to edge without privacy consideration. Therefore, considering both privacy and resource consumption, we choose to keep only one fully connected layer at the device, and the remaining 5 layers are offloaded to the server. Is our best practice. In the next part, we would introduce the trade-off between accuracy and privacy preservation. Let's focus on the green part in this figure. In this model, we follow the federated learning paradigm, a novel distributed machine learning technology. With federated learning, participating mobile devices train their data locally and exchange the model parameters rather than the local data to establish a common model. Specifically, in our design, we aggregate models from the distributed hospital servers at the cloud center to form a healthcare network. Different from existing efforts on federated learning, we aggregate the latter part of medical model that is deployed at the hospital private servers instead of the whole servers. The reason is that exposing the structure, parameters, and the results of the formal part of the model at the same time would fascinate the attackers to breach user data on the mobile device. As a result, the cloud data center needs to take a few more rounds of interactions with distributed hospitals for the virtual common model to obtain various data characteristics and make accurate diagnoses for users. We distribute that breast cancer gene samples among 100 hospitals, and we follow existing works to make that data non-independent and identically distributed in multiple hospitals, which is practical. We test and analyze the performance of the 3D models on the different learning paradigm. We repeat the experiment 100 times and statistic their performance distribution. Their performance is shown in these figures. We select F-measure and accuracy as our model evaluation metrics. We could find that centralized learning, which collects all data in the cloud and performs centralized training, has the best performance but no privacy protection. Standalone learning, which performs local training without collaboration for security, has a strong privacy protection but poor performance. Or proposal without low data leakage to any third party could achieve near optimal performance. Besides, we further evaluate the performance of standalone learning and federated learning on the different data distribution. We found that the federated learning performs better than standalone learning in the context of distributed private data. In the last part, we also discussed the trade-off between accuracy and privacy, but more emphasis on the external and internal risks faced by the mobile healthcare records. Let's focus on the blue part in this figure. In this module, we focus on strengthening the privacy protection in the healthcare network by the means of weakening the contribution of one single hospital and user in the model training process. As we described above, there exist two types of information interaction among the three entities. The first interaction is to offload training tasks from the mobile device to the hospital server. The second interaction is to aggregate models from the distributed servers. Considering the unreliability of cloud providers and healthcare providers, we should take more protections in their interactions. We propose to utilize Gaussian mechanism to perturb the interaction information and achieve the differential privacy protection. It could maximize the macro availability of data under the privacy protection of individual data samples. Here are our experimental results. Sigma 1 and Sigma 2 refer to the noise parameters in our two-stage differential privacy protection, respectively. We evaluate the sensitivity of Sigma 1 and Sigma 2 to the model influence in performance. As we can see in these figures, we could find that the performance gradually decreases with the increases of noise level. Considering both privacy and performance, we select Sigma E and Sigma 2 as 0.5 and 2.25 respectively. Finally, I would like to make a conclusion with this presentation. In view of the difficulty of applying artificial neural networks in mobile medical networks, we propose FEAR, a federated edge learning system for mobile device, to train medical machine learning models by securely and efficiently process the distributed private data in parallel. In this system, the mobile device offloads partial training and monitoring tasks to the hospital private server to improve the efficiency and the distributed hospital aggregate their models to build the global models to improve diagnosis quality with the guarantee that the data is still kept at user devices. Besides, two-stage differential privacy mechanism is applied to resist both the external and internal security risks, and the evolution proves our systems achieve our targets. Okay, that's all my viewpoints. Thank you very much for your kind attention. It's my first time to deliver a report at academic meetings. If I don't explain something clearly and you have any questions, I would be happy to answer it.